So here's question 6, right? This is a mass spec question, the obligatory mass spec question. This is another thing that the AQA have gone bonkers for recently, or since the A-level changed, I should say. So mass spec's always been a part of kind of what used to be called Unit 1, the Year 12 stuff, but it is a much bigger thing now in terms of the level of demand of the questions for calculation and also level of demand for the explanation. So we've got one question here which doesn't mention ionisation and it doesn't mention ion drift. So instead it kind of picks out some specific bits of the procedural part of the mass spec explanation. So we've got acceleration. So I'm going to split it into 3 parts, because that's what it's basically asking about. Okay. Acceleration, right? Ions, positive ions, right? You can have negative ions in mass spectrometry, but it's a completely different setting and mode, and it's not something that's covered at A level. So positive ions are attracted to a negatively charged metal plate. Okay, and actually it tends to be in the diagrams that you look for mass spec. It's actually more like a kind of series of plates with little holes in. And so the idea is that the positive ions kind of get focused into a beam, and this is the stage where they start to accelerate, where they get sped up. Okay, and so detection. Ions hit a negatively charged plate. So again, the sort of key thing here is you've got this manipulation of positive ions by negatively charged metal plates, and they accept an electron in this case. Okay, they accept an electron, they are discharged, meaning they get turned back into something neutral. And there's an equation for this, which you sometimes have to do. So let's say that, for example, chromium comes up in the next question. So let's say, for example, it's chromium. Your chromium plus ion accepts an electron and just becomes chromium. And the point about the detector plate is this electron here, the movement of that electron from the negatively charged plate into the sample, that produces a current, right? And that links to the next part of the answer, which I'm running out of room for, but I'll make do. Okay, and abundance, the amount of each ion, is proportional to the size of the current that's generated when the ion hits the detector. So what we're basically saying is the detector can tell when a particular ion hits it because it's measuring its time of flight, which doesn't get mentioned in this question, but that's what it's doing. So if lots of chromium plus ions, if lots of these hit the detector at the same time, you get a large current, kind of spike of current, and that is what the detector measures as a high abundance of that ion. If there's only a few of them, you get a lower current and therefore a lower abundance. Okay? Weird question really, because it kind of skips out this whole section, right? The bit that's in the middle that's not getting talked about is the whole flight tube section, which is really important. I guess they ask about it later probably, but it's just interesting that they skip that over. So then, we have another classic question here. If you're still looking at what's up there, you'll need to pause the video because I'm just going to get rid of the bottom part just to tidy up a little bit. Okay, that'll do. Right, this is another thing that they're really fond of at the moment. Calculate the mass in kilograms of a single ion of a particular mass number, and you're given all this other information. So they're nice here. They say to you, assume that the mass of a chromium ion with a mass number of 52 is the same as the atom. What they're basically saying is ignore the fact that it's lost an electron, because as we've kind of, as you should have learned when you first start chemistry, the mass of an electron is so small it's taken to be negligible. Even compared to the very small protons and neutrons, we still say that it's even smaller. So the fact that an electron has been lost is not going to influence the mass for this calculation. Something else that's absolutely crucial. you are given the Avogadro constant in this question, and in terms of technique issues, if you are given the Avogadro constant, you are going to need to use it. They do not give it you just for the sake of it. So if it's there, it's going to be somewhere in our working. Okay. Another thing to point out, our mass here has been asked for in kilograms. Okay. Now that's important because we're going to kind of essentially use a mole calculation, and moles is a quantity that's always relative to masses in grams. So there will be a little bit of unit conversion as well. Okay. So the relationships here, you can kind of spend a while trying to explore them, but the simplest way to put it is in a few different kind of contexts, right? Again, just tidying up a bit. So 52 is the mass number of this species, of this ion or atom. It's the same mass number whether it's the ion or the atom that we got told that. Okay? So one thing you're supposed to understand is the relative mass of any substance, whether it's relative atomic mass or relative formula mass, or in this case, because it's a single element, an isotope of an element, it's the mass number, still a relative mass. That, in grams, right, is equal to the mass of 1 mole. That's a fact you're supposed to learn because it's how moles work. It's one of the ways that the whole mole calculation is constructed. Why am I telling you this? Well, there's another fact that we're supposed to know, which is 1 mole equals 6.022 times 10 to the 23 particles, right? So in this case, our particles are ions. So that means that in 1 mole, there must be 6.022 times 10 to the 23 ions, because that's another fact you learn, right? And the Avogadro constant itself tells you that. 6.022 times 10 to the 23, it doesn't say particles, but that's what it means, per mole. That's what mole to the minus 1 means. Okay? Now, what I'm trying to get at here is, you get rid of the middleman here, and you can basically say that 52 grams must contain this many ions. So let's just clarify that. Okay, so 52 grams equals this many ions. We've just arrived at this fact because that's the mass of 1 mole, and that over here we have the number of things that is in 1 mole. So we're linking those two facts. Okay, so if you've got 52 grams of chromium 52, you've got 6.022 times 10 to the 23 ions, which is a lot. Okay, but it still doesn't even weigh that much. 52 grams is really not that heavy, and that's to do with the fact that particles like ions and atoms are generally very small. Okay, so how do we get to an answer? Well, we don't want to know the mass of 6.022 times 10 to the 23 ions. We want to know the mass of one of them. Okay, so the point about this again is we are looking for a very small number. All right, and before I even do the calculation, I'm going to point out the mass of a single ion is going to be something like that in grams, something like that in kilograms. There might be a little bit of variability up here. It might be times 10 to the minus 23, or it might be times 10 to the minus 26, but it's going to be something like that. It's going to be a really, really small number, right? And the reason I'm telling you that is it's for basic fact checking. If you're doing these calculations and you don't remember how to establish this relationship, you might just wildly bang some numbers into your calculator. Okay, right, that's not ideal, but at the same time, you're looking for something. You're looking for a really small number, because the mass of a single particle is really small, right? You have to have 6.022 times 10 to the 23 of these things to even get 52 grams, which isn't even that much. So the point is, you're looking for a really small number. To arrive at that really small number, right, there are two ways we can do this. What we can say is that 52 divided by Avogadro's constant, if we try that, right, 52 over 6.022 times 10 to the 23, then we get a dead small number, right? We get 8.64 times 10 to the minus 23. All right, so it wasn't times 10 to the minus 22, but it was close, times 10 to the minus 23. We still haven't got the correct answer though, because I mentioned something else earlier. Comes out in grams, Therefore, we need to divide by 1,000, right? In other words, we've got 8.64 times 10 to the minus 26. Just get rid of that for a sec. Kilograms. Okay, so that number up there was in grams. Our answer, which we're going to draw a box round or say, this is my answer, please mark that, examiner, right? That is our value that we want. It's actually a number that's not quite 8.64, but I've done it to 3 sig figs, all right, and that'd be completely fine. So then, below, we've got a linked question. So, in a time of flight, blah, 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 you can read it yourselves. We now need to use the equation k equals half mv squared, which we're always given in A level, although it's good to know it just because if you know it, chances are you know some of the rearrangements, and more often than not, you need them. Here's an example, right, because I'm going to have to rearrange this equation. So if you're a mathematician, you'll probably be totally happy with this and you don't really need the explanations, but let's just assume for a second that you don't do maths, or you were kind of less confident at GCSE maths. That's totally fine. You just need to spend a little longer getting up to speed with it for A-level chemistry. So we're given the kinetic energy, that's down here, that's a known number. Okay, we're asked to find the velocity, that's an unknown, and then the mass, well, we've just found that out. So it's actually a completely dependent question, right? You have to have the answer from the previous to get 2 marks. I suppose they might give you 1 mark for process if you haven't got an answer for the previous one, but they haven't even done that nice thing that you get in some past paper questions where they say, if you could not solve the previous question, assume that the mass of a chromium-52 ion is, and then give you a number which isn't actually correct, but allows you to score full marks. They've not even done that. So unfortunately, you need the mass from the previous question, right? So then, how are we going to rearrange this, right? There are several that you can learn, right? But again, let's just assume for a second that you're less confident. The easiest way to do this for now is to get v squared on its own, right? And the reason I'm saying that is because it involves the fewest steps. So v squared equals, and then I'm going to say ke divided by half m. That's one rearrangement. You can do this. You can take the kinetic energy and divide it by half of the mass, and then take the square root of your answer, right? So let's do that as our first route through. I've still got the mass in my calculator, so I'm going to leave it as the more precise number. I'm going to times it by 0.5, right, because that takes half of it. And then I'm going to bang in the kinetic energy, 1.269 times 10 to the minus 13, right? And then I'm going to divide by, and then use the answer button, which I mentioned in an earlier question. Okay? The number that I get is a really big number. That's because it's the velocity, which is going to be high anyway, because the ions do travel very quickly. But that's the velocity squared. So now I'm just going to do square root, and then I'm going to use the answer function again. And I get 1.71 times 10 to the 6. Doesn't come out in standard form, but that's what I've converted it to, meters per second. And that is a sensible answer. Again, once you've done a few of these questions, you get the sense of how fast the ions are going to be. So I didn't write any working there, okay? And that's because, there's a different rearrangement which we could do, but that's a completely acceptable answer. All right. Let's say that we want to do a little more work up front. All right. There's another way we can do this. So let's say we want v on its own, so we don't have to take the square root of it at the end. All we'd have to do is take the square root of both sides to get rid of the v squared, and it's just v, but that means you're taking the square root of v squared to get rid of the squared, but you're also taking the square root of the other side, so it's square root of ke over half m. This gives you exactly the same answer. The elegant one that appears in all the mark schemes, right, is a slight twist on this, which is, you can just learn if you want that the relationship here is v equals 2ke over m. This gives you exactly the same answer, because instead of there being half m on the bottom, right, there's now 2ke on the top. And just because of the way that the relationship works here, if you double the thing on the top, it's the same as halving the thing on the bottom. All right. So that's a completely valid alternative. So let's say that that's our version, right? V equals, and then we've got the square root of 2 times 1.269 times 10 to the minus 13, right? Divided by, And I'm going to use the rounded mass from the previous question because I don't have it in my calculator anymore, and I'm sure it will be absolutely fine anyway. So we do that in our calculator. 2 times 1.269 times 10 to the minus 13. So that's a little low energy. Divided by 8.64 times 10 to the minus 26. Then we take the square root of our answer, and we get the same thing. 1.71 times 10 to the 6 meters per second. Okay? It's not too tricky that. There are far worse ones than this, right? There are harder calculations than this in this kind of context. But it's important to remember that you're expected to do this rearrangement, but it doesn't have to be in exactly that way. You know, I showed you a couple of other ways. It's just that this is the one that the mark scheme's always having. Okay? Right then, another mass spec question. This time, it's a sort of patterning question, and I always tell my students when we're learning mass spec, we look at chlorine and the patterns associated with that, and I always tell them that you might well be asked about bromine as well, but we don't necessarily look at it. Depends how much time we've got. So this has come up before, right? Things that we need to talk about. All the stuff that's in this question. Mass numbers, they're going to be relevant because we're going to calculate the mass to charge ratio of the molecules. Equal abundance, that's going to be important. Just ignore the approximately because we're just going to treat them as if they're completely equal. And the fact that bromine is diatomic is also really important. So what we're basically saying is you've got the structure of bromine like that. You have two isotopes, 79 and 81, and they're approximately 50-50, right? 50% of one and 50% of the other, right? It's not quite that, which is why they've said approximately, but it'll do for this question. So what we're basically saying is there's a 50% chance that you can have one mass number or another in each atom. So let's have a look at the possibilities, all right? We've got 79Br, 79Br, okay? We've got 79Br, 81Br, and we've got 81Br, 81Br. Right, those would seemingly be our three possibilities. And so that means that there's going to be a peak at 158, there's going to be a peak at 160, and there's going to be a peak at 162. And that's correct. So that's one of your marks, is for putting something on the graph at those mass to charge ratio values. If you're not clear where they came from, it's the sum of 79 and 79, 79 and 81, and 81 and 81. That's where those numbers come from. However, we've neglected that there's actually a sort of fourth combination, right? So this was 158, this was 160, this was 162, this one is also 160, which means that the peak heights also need to be taken into account, right? So they have to be present in a particular ratio. This only appears once, this only appears once, but this appears twice, which means that the height of the peak at MZ 160 is going to be double the height of the other two peaks. Okay? So if we say that 158 goes like that to 50%, if we say that 160 goes to 100%, and 162 goes like that, that's the pattern it's looking for, like a 1:2:1 ratio for these peaks. It might actually be more accurate, I suppose, looking at this, to put it at 25, 50, 25, because that then adds up to 100%, although it doesn't really work that way. But let's just go with that, right? That's still present in the correct ratio. So it's quite tricky, that question, right? Because it requires you to think about all the possible different combinations of mass numbers in the molecule of bromine. And that tends to be as complex as it gets, although they do sometimes ask you about organic molecules that contain chlorine or bromine as well. Right then, so straight away here we've got another calculation. It is what I call a reverse relative atomic mass calc, or a reverse RAM calc. There's a little twist, which is they're asking you to calculate the missing abundance, which is not difficult, to be honest. It's just another thing to sort of throw in. So that's probably the first thing we should do, because we can't do a great deal of stuff without as much data as possible. And because this is a percentage, we know that these four numbers in this row of data have to add up to 100. So in other words, we've got 28 plus 25 plus 27. That's the abundance of everything except for the isotope. That's 80, which means that there must be 20% of the other isotope. Okay? So the number that goes in that box that I've put in green, 20. Alright? So then, that's going to be 1 mark probably. Let's have a look at what else we've got. We've got the relative atomic mass, and so this is one of those weird questions where you're not actually calculating the weighted average, you're doing a rearrangement of that sum. So 131.31 equals, and then we have to put in all the information that we've got, alright? So currently, let's see what we've got. We've got 129 times 28. Just going to bracket that. Add that to 131 times 25. Add that to 132 times 27. So all we've done so far is construct part of our weighted average plus m times 20. So we know that the abundance of this isotope up here is 20% now, but we don't actually know what the mass number is, and so that's what we're trying to calculate, right? That's all going to be divided by 100. So there's a bit more stuff we can do here. My first sort of protocol is to get everything on one line so we're not dividing anything, which means we have to multiply both sides by 100. So I'm trying to get this up here basically, right? Which means 131.31 times 100 is going to be 13,000 roughly. So we've got 13131 equals, and then I'm going to expand out all the brackets. 129 times 28, 3612 plus 131 times 25, 3275 plus 132 times 27, 3564, and then we've got plus m times 20, alright, or 20m I suppose you could write it as. So then, there's still a load of other stuff we can do here, right? Those big numbers that we've just expanded out can all be added together now. So that's all I'm doing is putting those three numbers together. So 13131 equals 10451 plus 20m. Right, let's write it like that now. I don't know why they chose m, I guess because it's mass number instead of x. And it's xenon, so maybe that's another reason why they did it, but it doesn't look right, it just looks a bit weird. Anyway, next thing to do, let's make this go over here, which means subtracting it from both sides. So 13131 minus answer in my case. The difference between those two things is 2680 equals 20m. So now we're down to something fairly simple. We need to divide both sides by 20 to get m on its own. I've still got this in my calculator, so divide by 20, m equals 134. Okay, let's go back and fact check. 134 was my answer. Yeah, that looks sensible, right? It's in line with the other mass numbers, 129, 131, 132. They should be pretty close together. They're never that different, right? They might differ by about 5, possibly even 10 at the most mass units, but they're never going to be wildly different. And that also sort of meshes with the average, which is, you know, if we think about all the numbers we've got, now that we've got all four isotope mass numbers and we know that the relative atomic mass is that number, again it sits in the middle of that range because all of these numbers are pretty close together. Yeah, 20 is the lowest of them, but it's got the right idea. So that's just a bit of basic fact checking without having to go back and, you know, review everything. Here's my answer, examiner, mark this bit please. You know, without having to go back and check everything, we've got a good idea of what we're doing. Alright? So, I'm going to pause before the next question.